All right, welcome everyone. My name is Willem Röpke, and today I will be discussing our paper, which was on commitment and cyclic strategies in multi-objective games. I haven't done this work completely by myself. I was helped by my awesome collaborators Oksana, Anne, and Diederik. If at any point during or after this presentation you have some ideas or some feedback or some questions, feel free to share them with me by sending me an email or by adding me on Twitter and just sending me a message there. Alright, so what am I going to talk about during this talk? Well, the paper that we've written really had a clear goal from the beginning. We wanted to study what is the impact of commitment in multi-objective games. And you see the two words and two concepts here highlighted in bold, commitment and multi-objective games. These are the protagonists of this talk, and I will discuss in a moment in more detail what they mean. And in our paper, we first performed a theoretical study. And in this talk, I will discuss with you the novel insights that we've gained from this and the main takeaway. So the things you really need to keep in mind if you want to move further with this research or if you want to maybe tackle some practical problems. And then afterwards, we've also done an empirical validation to explore the theoretical contributions in a learning setting. You might wonder, why did we do that? Well, it's one thing to know that something can theoretically happen, but it's an whole other thing to know if you can expect certain behaviors to really emerge in a learning setting. And I will share with you these results in this talk as well. So maybe a bit of background first. What are we studying and why do we think it's worth studying at all? Well, we're studying multi-objective normal form games. I've shown here an example. And intuitively, it's just the regular normal form game, but rather than getting scalar rewards, you get vector rewards. And to deal with these vectors, we assume a utility-based approach. And if you want to follow the notation, a utility-based approach assumes for each player I a utility function that maps vectors to scalar utilities. All right? And the way we incorporate this utility-based approach into our work is we assume that agents optimize for a scalarized expected returns criterion. Now, if you've never heard of this before, I will explain in the next slide with a quick example what it means. But just what it actually does is we care about the expected payoff from strategies, and players calculate the utility of their expected payoffs. All right? And why do we study this? Well, there are many real-world scenarios that you can think of that involve multiple agents as well as multiple objectives. An example that I've just come up with is this workshop. There are multiple agents here, namely all of the researchers, and we have multiple objectives. We want to share our research, we want to get some new knowledge, we also maybe want to network a bit, etc. Okay, so now I'm going to give you an example of this scalarized expected returns thingy if you've never heard of it in your life. And let's first take a step back. So what happens if you just have a single agent, a single decision maker? And they are confronted with a problem. You can choose to either go left or to go right. And left gives you a vector of 2, 0, and right gives you a vector of 0, 2. And your utility function is just to multiply your payoffs together. If you choose to always go left, you will just always get 0. And if you choose to always go right, you will also always get 0. But what happens when you take left 50% of the time and right 50% of the time? Now, first you need to take the expected payoff factor into account. So the expected payoff factor for left will be 1, 0, and for right will be 0, 1. So that gives you 1, 1. And now your utility will actually be 1. And so if we plug that back into our multi-agent framework, what this means is that we have agents that care about the expected payoff factor from their mixed strategies, and then we'll calculate the utility based on this expected payoff factor. Okay, and then moving on to the solution concept that we consider in this paper, we have, of course, the Nash Equilibrium. And if you are not familiar with this, it's a joint strategy where no agent can improve their utility by unilaterally deviating from the joint strategy. And we also consider cyclic Nash equilibria, which were first introduced actually in the context of Markov games, but they can also occur in multi-objective games. And what this is it's when no agent can improve their utility by unilaterally deviating from the joint cyclic strategy. And a cyclic strategy is actually a non-stationary strategy through which an agent continuously cycles. All right, so now we're coming to the interesting parts. Let's talk a little bit about commitment. So what is commitment? It's when one or more players commit to playing a specific strategy beforehand. All right? And then the other players can condition their own strategies based on this perceived commitment. So just as a quick example, let's say I'm playing a game with someone else, and I'm the leader, and I'm going to commit to playing action A. Then the other player, who is then the follower, can take this commitment into account and decide their best response based on my commitment. We can also come up with equilibrium concepts for this setting. Specifically, it's called a leadership equilibrium, and it's when the leader can't improve their utility given that the follower plays the best response. And I've put there in brackets that this is the definition for two-player games. Why don't we study this for more general games, for n-player games? Well, in that case, the definition and the theory becomes a lot more complex. So for now, we just focus on two-player games. If you look at the last couple of words of the definition there, follower plays a best response. That actually hides still a lot of complexity, because as you probably are aware, best responses are not unique. There might be a number of different best responses. And so we have to differentiate between two types of leadership equilibria, namely weak and strong leadership equilibria. And they respectively prescribe how an opponent selects their best response. So if an opponent selects the best response, which is worst for the leader, it's called a weak leadership equilibrium. And when they select their best response, which is best for the leader, it's called a strong leadership equilibrium. All right, so moving on to our own theoretical contributions. In single objective games, we currently have a lot of guarantees for commitment. And one of the main goals that we wanted to accomplish with our paper was to see if there is a way so that we can lift these guarantees so that they also hold for multi-objective games. And maybe the most important guarantee that we currently have in single objective games is the fact that optimal commitment is guaranteed to be as good as just playing a Nash Equilibrium in the game. But sadly, we discovered that this guarantee does not hold in multi-objective games. Specifically, if a player commits to a strategy, a malicious player might very well exploit this so that the leader actually ends up with a worse utility than before. Now, this has implications for a range of real-world scenarios. Specifically, one example that we came up with was in a leadership game between a regulation authority and an industry. This is almost by definition a leadership game because the regulation authority has to publicly commit to a set of regulations. And now what this implies is that if they try to maybe optimize for different objectives at the same time, there is a very real possibility that they will end up with a worse utility than if they hadn't committed anything at all, because the industry might be able to take advantage of this commitment. And to hopefully balance the scales a little bit, we also found that commitment can be strictly better than all of the Nash equilibria in the games. And this might be a little bit unintuitive at first, but the way this works is because commitment can help you avoid what we called the fixed point death trap. And I provide here a small example. Let's say here you have a single objective game where AA is a Nash equilibrium, right? So this is because black can deviate to B and red also cannot deviate to B. If you turn this into a leadership game and red is the leader, this becomes the leadership equilibrium. And you can see that red now gets a utility of 2, which is actually strictly better than before. And you might ask, is this not a Nash equilibrium? And the answer is no, this is not a Nash equilibrium. Why not? Well, if they were playing this game simultaneously and red knew that black was going to play B, then red actually has an incentive to go and play A. But if red plays A, then B has an incentive to also play A. And this way you actually end up in this fixed point death trap, and having commitment can help you avoid this. So the next thing that we did was, what happens when you commit not just to a regular strategy, but to a cyclic strategy? And it actually turns out that commitment to a cyclic strategy may be optimal. It may be the best thing for you to do. But this actually introduces some additional complexities. Why? Because if you ever wanted to figure out an algorithm or a learning method to learn optimal commitment, you now also have to include in your analysis if this is able to figure out the optimal cyclic strategy to commit to. And then the next thing that we looked at was, is it possible that a cyclic Nash equilibrium exists when no stationary equilibrium exists? And actually here the answer is yes, that's possible. And so what this implies is that even if you thought at first there is no stable solution in my game, stable solutions can actually still exist in the form of cyclic Nash equilibria. And this provides a valid alternative for the goal of a learning algorithm. Because in single objective games, learning algorithms, very often they try to implicitly learn a Nash equilibrium. Now, in multi-objective games, we know that Nash equilibria are not always going to be there. But if they are not there, maybe then it's worth devising a learning algorithm that tries to learn a cyclic Nash equilibrium. Okay, so what are the main takeaways of our theoretical contributions? Well, first, it's important not to underestimate that the theory becomes considerably more complex in multi-objective games. The guarantees don't just simply roll over, and we need to really take a look at everything again. And the utility from commitment can be better or worse depending on the payoffs of the game and depending on the utility functions that the players have. And lastly, only considering stationary strategies is not enough. Sometimes it will be the best thing for you to do to commit to a cyclic policy, but you also have to take this into account if you ever want to devise an algorithm that computes or learns optimal commitment strategies. Alright, so moving on to the last section of this talk, the empirical validation. So if you recall from the beginning, I've said that in the paper we really tried to evaluate all of the theoretical contributions that we've made to see if we can observe them in real actual learning settings. And to do this, we've had to come up with two new algorithms based on previous work. The first one is called the Pessimistic Follower, and it's intended to try and simulate a follower who is going to minimize the leader's utility. So it works by the leader committing to a mixed strategy and the follower who is going to try and play a strategy that they believe will minimize the leader's utility. And the second algorithm is called the non-stationary algorithm, and this is meant for players to be able to learn the optimal non-stationary strategy to commit to. All right, and how does this work? Well, you have the leader who is going to try and learn a simple mixed strategy, but we are going to force them to sample a pure strategy to commit to in each round. So that effectively means that they are going to play a non-stationary strategy consisting only out of pure strategies. All right, and the follower is then going to try and learn a best response to this entire non-stationary strategy. If you want to have a deeper dive into the code, it's freely available online. So the first question that we asked ourselves, can commitment be exploited by a pessimistic follower? And the answer, very sadly, is yes. If you look here at the dotted line, that line signifies the lowest Nash equilibrium in the game. And if you then look at the utility for the leader, you see that it's well below the line. So pessimistic followers are a real threat, and it's something that we should really keep in mind going forward if we ever wanted to use some of these things in a practical application. But the second question that we asked is, can commitment also just be better? And the result here is also yes. If you consider the game left, in this game the optimal utility is approximately 20. And you can see that for both players, they quite quickly reach this utility, so employing commitment in your learning problem can result in higher utilities for everyone involved. And lastly, we asked a new question. We said, okay, we know that sometimes commitment to a cyclic strategy is the best thing to do. Can we actually use and leverage commitment to be able to learn cyclic Nash equilibria in these games? And the answer here is complex, because it's unpredictable what is going to happen when followers have multiple best responses. Now, why is this? This actually makes quite a lot of sense. If I tell you that I'm going to do A, and the cyclic equilibrium would have you also playing A, then I can't know for sure that you're going to do that if you have another best response. I can't know for sure that you are going to follow along with my cyclic equilibrium. Now, on the other hand, under the right circumstances, it can still be reliably learned, as you can see here on the right side. If there is only one best response, over multiple trials, we found that the cyclic Nash equilibrium is exactly what is being learned. Alright, so that concludes our talk. To quickly summarize, we've highlighted the theoretical caveats in commitment. We've also evaluated these caveats in a learning setting, and we found that all of the theoretical contributions that we've made are clearly visible in these learning settings, so we should keep that in mind going forward. And for the future, there is still a lot of interesting theoretical questions to pursue. The first one that comes to mind is, when can we actually guarantee that commitment cannot be exploited? Because that's a very important question to ask ourselves. And then the next one is, what is the link between correlated equilibria and hierarchical equilibria? Because in the paper, we've mentioned this quite a few times, that there are a couple of links, and we see that these links really reappear multiple times, so this is worth studying. And also, how do we extend Stackelberg games to n-player games? And there are also some open computational problems, For example, is there an algorithm for learning or computing optimal commitment strategies? And how do we learn hierarchical strategies? And that concludes this talk. I hope you enjoyed it. And if you have any questions, ideas, or insights, please shoot me a message. And I see you all next time. Bye.